We're now starting chapter 9, which is focused on estimating the value of a parameter. And in section 9.1, we're estimating a population proportion. This would be the proportion of people that answer a specific way to a survey question, or when making observations, the proportion of people, the proportion of observations that match a specific characteristic out of the whole population. We'll be looking at these individually, so I'm not going to go through these, but you can pause and read them if you like. So the first objective is to obtain a point estimate for the population proportion. A point estimate is the value of a statistic that estimates the value of a parameter. For example, the point estimate for the population proportion is p hat, which equals x over n, where x is the number of individuals in the sample with a specific characteristic, and n is the sample size. Let's look at an example. The Gallup organization conducted a poll in which a simple random sample of 1,015 Americans 18 and older were asked, do you consider the amount of federal income tax you have to pay is too high? Of the 1,015 adult Americans surveyed, 458 said yes. Obtain a point estimate for the proportion of Americans 18 and older who believe the amount of federal income tax they pay is too high. So substituting the values that we get into the formula, specifically the number of people that responded with this characteristic that their taxes are too high versus the total of people in the sample, gives us the population proportion, which is 0.451. We estimate that the proportion of Americans 18 and older believe that the amount of federal income tax they have to pay is too high is 0.451. So notice this is just a sample, and this is how surveys are done, right? So you survey a group of 1,000 people, and then you make some kind of inference about that number relationship to the total population. So we sampled 1,015 people who said their taxes are too high. Oh, there's 300 million Americans. I don't know how many of those are adults. Let's say 200 million. Then we're saying that just below half of them, 0.45 of those 200 million Americans, so just a little bit below 100 million, think they're paying too much in taxes. Our second objective is to construct and interpret a confidence interval for the population proportion. In statistics, we construct an interval for a population parameter based on a guess along with a level of confidence. The guess is what we just figured out, which was that point estimate. So we've taken a sample, we've got a proportion from the sample, and so we're guessing that sample proportion works in the entire population. So although we only surveyed 1,015 people in the last example, we're saying that proportion of 0.451 probably correlates to the population as well. Now the part about this, the second part of this, is the level of confidence. Okay, and so that's where when you see surveys, if you watch any on the news, especially around elections and things like that, they'll say that this survey has a margin of error of plus or minus 3% points or something like that. And so this is kind of connected with the level of confidence about how wide that interval should be. Okay. A confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. Okay, so we said 0.451 is the parameter, or our guess at the parameter for the number of people who think they're paying taxes too high in the total population. And then that confidence interval would be like based upon how confident we are in that number, maybe how many samples we took, etc. We give that kind of interval above and below the 0.451. The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. And the level of confidence is denoted as 1 minus alpha times 100%. For example, a 95% level of confidence, which would equivocate to alpha equaling 0.05, implies that if 100 different confidence intervals are constructed, each based on a different sample from the same population, we will expect 95 of the intervals to contain the parameter and 5 to not to include the parameter. Well, you can imagine a 95% level of confidence. If you're 95% confident, that means that, I hate to use the same word, you're very confident that the results that you get, you're going to get again and again. So, and really that they're going to apply to the whole population, not just to that sample. So as you can see, as a confidence level goes up, you have a much stronger belief in the validity of your statistics or parameters. Reviewing what we know about the model that describes the sampling distribution of p-hat, the sample proportion, we're going to look at how to construct a confidence interval. The shape of the distribution of all possible sample proportions is approximately normal, provided that n times p times 1 minus p is greater than or equal to 10. And what this is saying is that the sample size is no more than 5% of the population size, and the data are obtained randomly. So that's the first check. Do we have a sample size that's not bigger than 5% of the population, and do we collect data randomly so that nothing's been set up? The mean of the distribution of the sample proportion equals the population proportion. That is that mu sub p hat is equal to p. And the standard deviation of the distribution of the sample proportion, the standard error, is sigma sub p hat is equal to the square root of p times the quantity of 1 minus p all over n. So looking at this figure 2, because the distribution of the sample proportion is approximately normal, and remember what we mean by normal is it's just this bell-shaped curve. It kind of connects with the concept of the empirical model and the different percentages that fall within 1, 2, and 3 standard deviations. Remember those from the empirical rule. We know that 95% of all sample populations will lie within the 1.96 standard deviations of the population proportion P, and 2.5% of the sample proportions will lie in each tail. Okay, so we get 95 in the middle, and then 2.5 on each side, so that gives us another 5, making it 100%. It is common to write confidence interval estimates for the population proportion as point estimate plus or minus the margin of error. And this is what I was speaking to before, that when you see surveys, especially political surveys or anyone that's doing surveys and publishing them, will usually give their margin of error plus or minus 3% points, etc. And this is some indication of the confidence level. So if you have a smaller interval, then your confidence is much higher, right? If you have a large interval, then your confidence is not so high. The margin of error for a 95% confidence interval for the population proportion is 1.96 sigma sub p hat. This determines the width of the interval. To visually illustrate the idea of a confidence interval, we've drawn the sampling distribution of p hat. Now create a slider that shows p hat at plus or minus 1.96 sigma sub p hat. As p hat leaves the blue shaded region, the corresponding confidence interval does not capture capture the population proportion. Okay, so notice what we're saying here is the confidence level works for the data in this blue range and not for outside the blue range, which is that plus or minus 1.96, the standard deviation of p hat. The figure tells us that for a 95% confidence interval, 95% of all sample proportions will result in a confidence interval that includes the population proportion. That's here. While 5% of the sample populations, those in the tails, will result in a confidence interval that does not include the population proportion. Let's illustrate what 95% confidence means in a 95% confidence interval in another way. If we simulate obtaining 200 different random samples of size n equals 50 from a population with p equals 0.7, the figure on the next slide shows the confidence intervals in groups of 100. A green interval is a 95% confidence interval that includes the population proportion p equals 0.7. A red interval is a confidence interval that does not include the population proportion. For now, ignore the blue intervals. I know these are hard to see as far as I can see a lot of green, I can see some blue on the edges. It's hard to see a lot of the reds. So let's add some details here. Notice that the red intervals do not capture the population proportion 0.7, have centers that are far away, more than 1.96 standard errors from 0.7. Of the 200 confident intervals obtained, 10, which are the red intervals, do not include the population. For example, the first interval to miss has a sample proportion that is too small. It's right here, so it's pointed out here, to result in an interval that captures 0.7. The second interval to miss is it's pretty close, it's down there, has a sample proportion that is too large to result in an interval that captures 0.7. So 190 over 200, which equals 0.95. This indicates 95% of the samples have intervals that capture the population proportion. So a 95% level of confidence means that 95% of all possible samples result in confidence intervals that include the parameter, and 5% of all samples result in confidence intervals that do not include the parameter. Be careful now, a 95% confidence interval does not mean that there's a 95% probability that the interval contains the parameter, such as the population parameter or mu, the mean. Remember, probability describes the likelihood of undetermined events. Therefore, it does not make sense to talk about the probability that the interval contains the parameter, since the parameter is a fixed value. Think of it this way. I flip a coin and obtain a head. If I ask you to determine the probability that the flip resulted in a head, it would not be 0.5 because the outcome has already been determined. Instead, the probability is 0 or 1. Confidence intervals work the same way. Because p or mu are fixed quantities whose value is unknown, we do not say there's a 95% probability that the interval contains p or mu. Instead, the probability that the interval includes the parameter is either 0, the interval does not include the parameter, or 1, the interval includes the parameter. The value of the sample statistic. Whether a confidence interval contains the population parameter depends solely on the value of the sample statistic. Any sample statistics that is in the tails of the sampling distribution will result in a confidence interval that does not include the population parameter. Okay, so that's when it's out on those outer edges beyond the 1.96 standard deviation. It does not include the population parameter. It's too far out. You might think of it like an outlier to some degree. So as far as the interpretation of a confidence interval, a 1 minus alpha times 100% confidence interval indicates that 1 minus alpha times 100% of all simple random samples of size n from the population, whose parameter is unknown, will result in an interval that contains the parameter. It is between those 2 points, the mu plus or minus 1.96, the standard deviation. A 90% confidence level of confidence does not tell us there's a 90% probability the parameter lies between the lower and upper bound. 1 minus alpha times 100% of all sample proportions will result in confidence intervals that contain the population proportion. The sample proportions that are in the tails of the distribution in the figure will not result in confidence intervals that contain the population proportion. And so you can see that here in this diagram. So the 1 minus alpha times 100% is the actual proportion or that contains the parameter. The 5% on each end, it's that alpha over 2 times 100%, because we're splitting the 5%, 2.5% on each end. All right. I feel like we're saying this again and again in many ways, hopefully kind of so that you will be able to interpret it and understand. Next, we're going to look at the critical value. The value z sub alpha over 2 is called the critical value of the distribution. It represents the number of standard deviations the sample statistic can be from the parameter and still result in an interval that includes that parameter. Remember, we're trying to identify data from the sample that we can use to make inferences for the entire population. And so this critical value, again, is representing the number of standard deviations away from our statistic that we have from our parameter and still apply to the population data point as well. Table 1 shows some of the common critical values used in the construction of confidence intervals. Notice the higher levels of confidence correspond to higher critical values. As the confidence level goes up, the critical value goes up. So you can be further away from that data point and still have confidence that you can make a inference about the population data as well. Okay. And I like how this table builds. You've got the level of confidence, right, which is the 1 minus alpha times 100%. Then we have the area in each tail, right? That's depending upon our level of confidence, whatever that alpha is, right? So if we have a 90% confidence level, that gives us an alpha of 0.1, right? Okay. Or 10%, you might say. And so alpha over 2 would be 10%, or 0.10 divided by 2 of 0.05, and then that critical value is 1.645, okay. So this lecture is about 40 minutes, so it's a good time to take a break, get up, get a drink, get a coffee, walk outside, take a 15-minute break, and then come back and finish the lecture. So let's look at an example. When the Gallup organization conducted the poll introduced that we looked at earlier, 45.1% of those surveyed considered the amount of federal income tax they have to pay is too high. Gallup reported its survey methodology as follows. Results are based on telephone interviews with a random sample of 1,015 national adults aged 18 and older. For results based on the total sample of national adults, one can say with 95% confidence that the maximum margin of sampling error is 4 percentage points. So our question is to determine and interpret what this confidence interval means for the proportion of Americans aged 18% who believe that their federal income tax they pay is too high. Okay. So the point estimate, this is the proportion that we had in our sample, the number of respondents who said that their taxes are too high over the total number of respondents. The point estimate is 0.45, and the margin of error is 0.04, and that's given in their report of its survey methodology here, 4 percentage points. The sampling error is 4 percentage points. The confidence interval then is 0.451 plus or minus that margin of error. And so we have a lower bound of the confidence interval, which is the minus, the difference, which would give us 0.411. And we have the upper bound of confidence as being 0.491. So we are 95% confident that the proportion of Americans aged 18 and older who believe that the amount of federal income tax they have to pay is too high is between 0.411 and 0.491. So really between 41% and 49% of Americans believe their taxes are too high. Okay, and so that's the interpretation of a confidence interval. We just add or subtract the margin of error, and we get the upper and lower bounds. And so we're 95% confident that this statistic is applicable, not only that we got from our sample, that this is applicable to the population, to the entire population. Next, we're going to look at constructing a 1 minus alpha times 100% confidence interval for a population proportion. Suppose that a simple random sample of size n is taken from a population, or the data are the result of a randomized experiment. A 1 minus alpha times 100% confidence interval for p is given by the following quantities. The lower bound is p hat minus the critical value, z alpha over 2, sub alpha over 2, times the square root of p hat times 1 minus p hat over n. And the upper bound is that same formula, but instead of a difference, it's of course addition. Okay. Our margin of error is simply the plus or minus figure that you see here, plus or minus, right? And that's our critical value times the square root of p hat times 1 minus p hat over n, which is of course our sample size. And always, as we've been talking about, in order to construct this interval and for it to be valid, we have to make sure that our sample size is appropriate, that it is not more than 5% of the population. Okay, and that's what you see here in this last one. And these are calculations that kind of confirm that. So we need to confirm both of those. Okay. So let's look at this. Let's look at an example. In the Parent-Teen Cell Phone Survey conducted by Princeton Survey Research Association International, 800 random sampled 16 to 17-year-olds living in the U.S. were asked whether they would ever use their cell phone to text while driving. Of the 800 teenagers surveyed, 272 indicated that they text while driving. Obtain a 95% confidence interval for the proportion of 16 to 17-year-olds who text while driving. Okay. First, we're going to do this by hand, and then we'll look at StatCrunch. Since there are 272 respondents who do text while driving, then our p hat is that statistic, that proportion, that statistical proportion of the number who responded over the number in the sample. And so we get p hat equals 0.34. Okay, that's our population proportion. The individuals were obtained through a random sample. Again, we got to confirm this, so we plug in the numbers. N is 800. P hat we just figured out is 0.34 times 1 minus 0.034, and we get 179, which of course is greater than or equal to 10. We can assume that there are, well, here this says there's more than 1 million teenagers 16 to 17 years of age in the US. So our sample size is definitely less than 5% of the population. Because our calculation here is greater than 10, and because our population is less than 5% of our sample size is less than 5% of the population, our independence requirement is satisfied. The next thing we have to do is we want a 95% confidence level. So we have alpha, which of course equals 1 minus the confidence level, which gives us an alpha of 0.05. So our critical value, z sub alpha over 2, is z sub 0.25, right? 0.05 divided by 2. And this equals 1.96. This is what we saw from the table 2 slides back. Okay, the confidence intervals connected to the critical values. All right. So if we substitute this into formula with n equals 800, we can obtain the upper and lower bounds of the confidence interval. And so here are those calculations here. Our p hat minus our z sub alpha, our critical value times our calculation of p hat over 1 minus p hat over n. And we get 0.307 for the lower bound where we're subtracting them. And we get 0.373 when we're adding that margin of error. Okay. To find out our margin of error, it's the value that we're adding and subtracting it to find the bounds, and you can see that calculation, 1.96 times the square root, blah, 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 is 0.033, and so this is our margin of error that's right in that formula. So we are 95% confident. We are 95% confident, that was the parameter we were given, that the proportion of 16 to 17-year-olds, this is the population proportion, is between these two values. So it's between 0.307 and 0.373. So roughly we're saying between 31 and 37% of 16 to 17-year-olds who text, of all teenagers 16 and 17, text while driving. If we look at the technology solution, step 1 and step 2, calculating p hat, and step 2, determining independence, are the same as by hand. So I'm not going to repeat these here. You can go back 2 slides and see that. So what we do is we look at the data from StatCrunch, and we can see here that this is actually calculating parts already for us. And so we get the upper bound is 0.307. I'm sorry, the lower bound, lower limit. The lower bound is 0.307. The upper bound is 3.728, which is 3.73. So these are both the same. And the margin of error is found by determining the difference between the point estimate, which is right here, right, and the upper bound. So we get 0.373 minus 0.34 is 0.33. So again, the way we state this is that we are 95% confident that the proportion of 16 to 17-year-olds who text while driving is between 0.307 and 0.373 of the entire population of those teenagers. Okay. So we had a relatively similar, I can't remember if the margin of error is a little bit different or not, but we have good stats here that correlate both to our technology solution and our by hand solution. So we're looking now at the effect of the level of confidence on the margin of error. And as we pointed out before, that a higher level of confidence leads to a wider interval. So let's look at a problem Let's go back and look at a problem, the same one we just did, when we estimated the proportion of 16 to 17-year-old teenagers who text while driving. And we want to determine the effect on the margin of error. The last problem was at 95%. So let's increase the confidence level, the level of confidence from 95 to 99%. With the 99% level of confidence, alpha will equal 0.01, right? 1 minus 0.99. So to compute the margin of error, we determine the critical value of z sub alpha over 2 as z sub 0.005. That's just 0.01 divided by 2. So we get z sub alpha 0.005, and this is the value that was given in the table several slides back. We had three. We had a 90% level, a 95% level, and a 99% level. Substituting these values into the error formula of the critical value times the square root of p hat times 1 minus p hat. Remember, p hat from the last example was 0.34. That was the proportion of the sample. Okay, and so we get an error rate of 0.043. Since the margin of error for the 95% confidence interval was 0.033, we can see that increasing the level of confidence increased the margin of error, resulting in a wider confidence level. So what this is saying is that we can increase that level because, again, a higher confidence level gives us a wider range of values that we can include as far as reporting that data. Here we have a 99% confidence interval using the TI-84 plus C graphing calculator. And here we can see that p hat is 0.34, the sample is 800, etc. We're given the lower and upper bounds in here. The lower bound is 0.297, the upper bound is 0.383. The midpoint is 0.34, which is our p hat value, which you can see there. And so to calculate the margin of error, we just subtract that from the upper value, or we could do it from the lower value. It doesn't really matter, but we can see here that we got the exact same value that we got in the last solution, which we did by hand, again proving that if we raise the confidence level, we get a wider margin of error. So what is the effect of the sample size on the margin of error? We know that a larger sample size produces more precise estimates. That's from the law of large numbers in Chapter 5. Given the margin of error formula, we can see that increasing the size of n decreases the standard error, because this number, the fraction is going to be, this is going to create a smaller and smaller fraction. So it's going to decrease the standard error as we multiply the critical value times a smaller number. So the margin of error decreases. This means that the larger sample sizes will result in narrower confidence intervals. Our last objective is to determine the sample size necessary for estimating a population proportion with a specified margin of error. Here we see the formula for calculating the error. Sample size needed for a specified margin of error would seem to be an easy algebraic manipulation of that formula that we see above, just simply solving this formula for n, dividing both sides by the critical value z sub alpha over 2, and then squaring both sides gives us this formula. But there's a problem here, because this formula relies on p hat, which p hat relies on n, so we are using a factor which relies on the factor we're trying, or the variable we're trying to calculate. So we really have two possible solutions in order to determine the sample size necessary for estimating a population proportion. within a specified margin of error. The first one is to use an estimate of p-hat. This would be based on a pilot study, so you would do a pilot study, or there was a previous study that you might use that proportion, okay? The second option is simply to let p-hat equal 0.5, which gives the largest possible value of n for a given level of confidence and a given margin of error. So again, we can either use a prior estimate, we can use an estimate based on a prior study or a pilot study we conduct, or we can simply set p-hat equal to 0.5. The sample size required to obtain a confidence interval with p with a margin of error e is given by the formula below. This is always rounded up to the next integer. Okay, now this is not normal rounding. Whatever the next integer value is, we go to it. So you don't have to, this is not a rounding where you see if the value of the decimal is above or below 0.5. Okay, we just simply round to the next whole number or integer value. So this is the formula we use where p-hat is a prior estimate of p. If we don't have a prior estimate of p, the sample size required is calculated as below. So we have two different calculations. If we're using a prior value of p-hat, notice the formula is just that simple formula we calculated. But if we don't have that prior value of p-hat, then we simply use this formula from below. Notice the margin of error should always be expressed as a decimal when using the above formulas, not a percentage. So let's look at an example. An economist wants to know if the proportion of the U.S. population who commutes to work via carpooling is on the rise. What size samples should be obtained if the economist wants an estimate within 2 percentage points of the true proportion with 90% confidence if A, the economist uses the 2009 estimate of 10% obtained from the American Community Survey. So let's do part A first, and then we'll come back to B. So part A, we can see the arrow is 0.02. This is the 2 percentage points, an estimate. They want an estimate within 2 percentage points, so that's your margin of error. Our alpha is 0.01 because we're looking for 90% confidence, so alpha is 1 minus the confidence. 1 minus 0.9 gives us 0.10. And our z is, our critical value is z sub alpha over 2. Well, if alpha is 0.1, 0.1 divided by 2 is 0.05. And then from the table, we see that z 0.05 is equal to 1.645. So we can plug those values into the formula we saw on the prior page, and we get a confidence, a sample level of 608.9, which we round up to the next integer value of 609. So using a prior p-hat value from a prior survey or study, the economist must survey a minimum of 609 randomly selected individuals. Well, what if the economist does not have any prior estimates? Well, all these values are going to be the same. Our error rate is 0.02, our alpha is 0.1, and our critical value is 1.645. Here we plug in the values, and notice we get a sample size of 1,691.3, which we round up to 1692. So the economist must survey 1,692 randomly selected residents of the United States. This is a huge jump, right? The effect of not having a prior estimate is that the sample size is more than doubled. And this I think it makes some good logical sense, right? So if you don't have a benchmark to use, you need to have a larger sample to ensure that your information is more accurate.